Okay, so in this video we're going to take a look at the idea of conservation of energy. So this principle says that the total energy of an object, or in fact a whole system of objects, stays the same unless work is done on the object by an external force. So let's digest that a little bit. So first thing is the weight force of an object is considered an internal force. So we don't consider the weight force of an object as causing its energy to change. Okay, so that's the first thing. But some examples of external forces that do cause an object's energy to change, things like drag and friction act to decrease the energy of an object, and things like thrust forces, etc., that we get with engines would act to increase the energy of objects. So we can model the conservation of energy using an equation. It says the work done is equal to the change in GPE plus the change in kinetic energy. And we'll see a few scenarios where this is used. So just to flag this up, the delta is the mathematical symbol for change. And a change is always calculated by subtracting initial from final. And that's going to be important in terms of getting our signs right later on. We've also been referencing work done, so let's talk about exactly what that is. Work done is the force multiplied by the distance the object travels parallel to the force. So W equals FD is how we usually express that. Okay, so that's some general background stuff. Let's dig into that one a little bit more. So let's say we have an object traveling with initial velocity u, so you can see that on the diagram it's going straight up the page, and has a force applied for a period of time. And at the end it has final velocity v. And in this scenario the force is acting perpendicular to the velocity initially, so you can see its direction is going to change, and then also we're all going to get a speed change later on when the force is no longer perpendicular to the velocity. Okay, so the key here is if we want to work out how much work is done, we need to multiply force by the right distance. So which distance should we use? Well, it's this distance here, and it's because that is the distance the object has moved parallel to the force. Okay, and that's the one that you need to use in this equation. That's why we'd use D3. Okay. So let's go back to something that we've met before, the idea of an object in uniform circular motion. So in this case, the resultant external force is directed towards the center of the circle, but the object never actually moves closer to the center of the circle. It stays at the same radius the whole time. And therefore, there is no work done by the force because it has experienced traveled a distance of 0 parallel to the force. And this is why if you're traveling in a horizontal circle, which means your GPE isn't changing, the kinetic energy and therefore the speed stays the same. Because if there's no work done, there's no change in GPE, there cannot be a change in kinetic energy either. Okay, so let's have a look in more detail at GPE, or more specifically change in GPE, because we can never really talk about the amount of GPE an object has, because for all different observers, objects have different amounts of GPE, so it's not a useful idea to talk about what it has. But what we can talk about is how much it changes. So when we say change in gravitational potential energy, what we really mean is the work done against an object's weight force to change its height. So you can see if we're moving upwards, we're doing work against an object's weight force, and we say that we've increased that object's gravitational potential energy. Okay, so if we have a look here, so if it goes from an initial height to a final height, we've got, or we could call that delta H. What we'd find out is, well, work done is force times distance, and the weight force of an object is mg, and the distance we've moved is delta h, or hf minus hi, and so that gives us how much GPE that the object has gained. Okay, so when we're looking at scenarios, we're going to be interested in changes in energy, because something's energy is pretty much never going to go to zero, but we can work out how much that energy has changed, and then we can work out what other forms it might have turned into. Okay, so that's gravitational potential energy. The other form of energy that we're going to use is kinetic energy, which again we're going to be talking about changes in kinetic energy, and it's the work done to change an object's speed. So if we apply a force to increase the speed of an object from an initial velocity u to a final velocity v, what we can do is we can say work done is equal to the change in kinetic energy, or final kinetic energy minus the initial kinetic energy. And kinetic energy is given by the equation half mv squared. So the work done is going to be half mv squared minus half mu squared, because it's final minus initial, and we can factorize out the half m to give us the expression here, half mv squared minus u squared. Okay, so a little thing at this point is to be very careful of is v squared minus u squared is not equal to v minus u squared. So don't make this mistake when you're doing some practice calculations. You square them separately and subtract them. Okay, so that's all very general, very non-specific. Let's actually have a look at some examples. So, an object falls from a height of 100 meters to the ground. The ball is initially stationary, and we'll ignore the effects of air resistance. Calculate the ball speed just before it hits the ground. So if we ignore air resistance, that means work done by external forces is going to be zero. There's no friction, it's not in contact with anything. There's no air resistance, so there are no external forces acting, because remember, its weight force is an internal force. The change in gravitational potential energy is going to be mg delta h, and it says we're going to go downwards by 100 meters. So the height change is going to be a negative number, so we get this minus 1000 m. The change in kinetic energy is just going to be half mv squared, because they're told the initial speed is 0, so u is 0. So putting that into our conservation of energy expression, we can see that 0 is equal to minus 1000 m plus half mv squared. We can rearrange that times by 2, divide by m, so you see the mass of the object actually doesn't matter at all, and we get the final speed just before it hits the ground, 45. So, you will often, however, see these questions done in a different way. So I want to show you how those examples as well, so you're familiar with both. So in scenarios where there's no work done by external forces, we will often phrase this or set this up as GP lost equals kinetic energy gained. So let's see that too. So the GP lost is 1000 m, so we don't have the negative sign in here because we've already got the loss part in the expression, so that's the same. So that GP gained is going to be half mv squared, again because its initial speed is 0. And if we equate those two things together, we can see we end up with the same expression we had before, and we end up with exactly the same final speed. So it's fine to set this question up either using GP lost is equal to kinetic energy gained, or work done is 0 and then you add them together and they get 0, and they both give you the same answer, so neither of these methods is better than the other.